Right. Before we begin today, let's just consider what the agenda is. We'll start off talking with we'll continue our discussions on complex analysis, and we'll start off talking about your contour, what essentially I want to cover what contour integrals are, and how they play a very crucial role in complex analysis, right? Before we do that, because see, contour integrals are where your electrostatics and everything comes into play. So the goal of this, throughout this, I'll give you several hints as to where electrostatics is coming in. But of course, further application into further application will require you to go into vector analysis and then see how it is applied in terms of vectors, and then come back to electrostatics. So basically, we'll just cover complex analysis and see how you can represent some sort of electrostatics in that. We won't exactly be solving problems in electrostatics or anything, but we'll try to see where the ideas of complex numbers, complex analysis, where it can be hinted to electrostatics, where it can be connected, right? So that's the end goal. With that end goal away, remember where we stopped last time. We stopped with this statement. Okay, let me open my screen before that. Screen share screen. Excel. We have this, right? Okay, so we have the we looked at. So yeah, this was taken in this was right? So we don't have those stuff here. We don't have our previous notes here. So anyways, we just talked about what it is to have a differentiable and analytic function in complex analysis, and then we realized we derived the Cauchy Riemann condition, right? So just to keep in mind, the Cauchy Riemann condition is that for the given that a function with so given that a complex function u of x, y plus I v of s, y is equal to f of g, where g is the complex number, that is x plus y. Then you have a differentiable function only if dou u by dou x equals to v by dou y, and dou u by dou y equals minus dou v by dou x. Right, so this was the condition that we saw, and to continue on this, we just look at a simple example. And so right now, what happens is, so let's look at let's consider the case where f of z is equal to z bar, right? So that means you have differentiation of x minus I y with respect to x plus I y, right? So if you notice, of course, right? So if you notice, as you trace along x plus I y, as you change x plus I y, is actually continuous, right? So depending on a function. So if you have a function of, so if so what we will prove right now, so what look at this statement, right? Is like, what do you see logically here? If you have x here and then iy here, then if this is g, then this is g, then g conjugate will be here, right? So now what do we see here? Can we differentiate z the conjugate with respect to z? Yeah, so it's not antithetical, right? So because like let's just look at this, right? So to prove this out, get this out of the way, we just see the so we just see that dou u by dou x is equal to 1. That is so because this is u and this is v, right? And then dou v by dou x is equal to minus 1, where our first condition is not satisfied, right? Wait. Oh, right. I think I made a mistake here. It's supposed to be, I think it's supposed to be dou u by dou x is equal to dou v by dou x, and then dou u by dou y is equal to minus dou v by dou y. So yeah, so that's just a little change of variables here. And it's just habit, right? So keep so right now, so what we have? We have the very simple fact that this function is not differentiable. It's everywhere. So if you take a analytic function of z, which is analytic everywhere, and then you say you change variables to f of z. This is continuous everywhere, but it's not differentiable with respect to z. So this is something interesting that occurs, like this is another element that you find in complex analysis and you don't find in real analysis, right? Like so why exactly is this, right? It's just because you have two orthogonal tangents. So when you try to measure f of, so when you try to measure this, like when you try to measure the tangent, you find that the tangents are with respect to z can be defined in two different ways. So whether you approach from the x, whether you like, so basically you have like a complex and a real part of the tangents itself. Like let's like so anyway, so it's not but the other point being that if you have g, right, g star is like a discontinuous jump. So therefore you don't really have like differentiation with respect to z when you have a function of z star. So yeah, so that being said, let's move on with what I wanted to cover today. So this is everywhere continuous but nowhere analytic. So such functions are everywhere continuous but nowhere analytic. So it's a very important result that like you'll come across later whenever you're dealing with functions in terms of z conjugate, right? So like then you need to remember that it's like you need to change the variables to z conjugate. Like you need to change the differential, you need to shift the frame. Like you have a discontinuous shift in terms of your like frame. So to make c star equal to c or something like that, so you have some sort of a shift and then you can like differentiate. But moving on, you have, so what the general solution of analytic functions in the complex plane follow what you have, what you call the Laplace equation. What are the Laplace equation? Delta of psi is equal to 0. So this is the Laplace equation. So wait, why is it? Okay, yeah. All right. So now how do you define this? This is defined by which is nothing but right. So how does this like, so if you look at this, then so the proof is very simple and obvious. So what you can do is you can just take just take d square u by d square is equal to so when you take this using the Cauchy Riemann condition, so you have dou square v by dou x dou y, right? So because you have dou v, so you're basically taking is equal to dou by dou x times dou y, sorry, dou v by dou y, right? Hey, wait, I think there's a mistake here. So essentially, right, okay, so let's see, I think this has to be right. So that's, yeah, so I think this has to be right. Instead of changing all of this, we should have just kept this as right. Anyway, so right, so we have is equal to dou square v by dou x dou y, and then you have this dou square u by dou y square is equal to dou square v by dou x dou y. Now just adding these two terms, right? So you have dou square u by dou x square plus dou square v u by dou y square, okay, which is basically you have dou square, you replace dou square with this, and you replace dou square by dou y square with respect to this. So you have basically plus and minus. So you have minus there, right? So dou square u by dou y square is equal to minus dou square v by dou x square. So then you have plus and minus, that is equal to 0. So essentially, so right. So this is the same process. So this proof is fairly simple, and yeah, of course. So, but a couple of interesting results apart from this, you have with respect to the Laplace equation. So when you take dou u by dou x dx plus dou u by dou y dy is equal to 0. We won't go into proving this, but just keep these in mind. And then we have dx dxu dxv plus dyu dyv is equal to 0. So where the d are in terms of like So you know the y components of the u functions and the y components of the v function. So it just so you have like the complex functions into u plus iv, right? So which is actually two separate functions. So if you can actually split it out, then you have, right, so your dx will be different from dy. So because the integral is going to be different based on, so integral of u dx is different from integral of u dy. So based on the integral, so again your integrals will be similar in certain cases. We'll come back to that later, but essentially, so this is equal to 0, right? So this actually has something, you'll find proof of this later when we talk about differential geometry, which is simply that d square is equal to 0, or d is equal to 0. I don't know why my zeros are coming half in when I share the screen. But yeah, it's like nobody wants, it's like the meat doesn't want me to complete my zeros. So anyways, so yeah, so this is something that we'll talk about later on. Just keep this in mind. We have something remarkable here, which is arising from a very simple fact that to meet like analyticity, your integrals and the differential derivatives have to be defined in a particular way. Then only are they analytic, right? So now moving on, this is we spoke about the gradients of a complex function, which is the sum of partial derivatives. But how do you take the total derivative of a function with respect to the variable? So you have, so because of this particular condition, because of the Cauchy-Riemann condition, you have a very simple definition for the total derivative, which is nothing. Can anyone take a guess? I mean, differentiation of the function with respect to what will give you the differentiation of functions with respect to like everything. Yeah. So you can just take this as df by that's it. So you don't need to complete your variable. Like I mean, you don't need a derivative with respect to y as well. You just have a derivative with respect to x, and that's like good enough, right? Why? Because as we saw earlier, the information encoded in the function about with respect to x is like also encodes the same information with respect to y because of the Cauchy-Riemann conditions, right? So you saw the equivalent. So that being said, this is something different from your ordinary differentiation, multivariable differentiation. So because in multivariable differentiation, you don't have this explicit relation. So you can't say your total derivative is only the derivative with respect to one particular variable. So you need to like take the derivative, like you need to take the gradient then. So with respect to when it comes to multivariable calculus. So so moving on, so let's try to derive let's try to derive explicitly so this serves as a homework, right? But let me, or do you want me to do it? Yeah, so it's essentially which we came across yesterday again. So this shall be the just work this example out and see where it's coming from, and so we'll move on to the next. So once we are done with our differentiation, we'll move on to contour integrals, right? I mean, basically integration. So how do you differentiate a function? Like how do you integrate a function, a complex function? It is same as differentiating a real function. So summation, when you have like summation n, here's the first, like you have summation of a real like piecewise function, right? So you have piecewise points, collection of points. So if you have points in your axis, I mean in your x-axis, so if this is function of that, so then you have x minus x naught, so x naught, x1, x2, so on until xn. So and then you take the summation, like the difference between each alternative points on the type. So similarly you have in complex integration, you have j equal to 1 to n summation of f of a high j so this gives you the this particular part gives you the difference between the 2 points, that is the and then this particular part gives you the value of the function, so that is the height. So you just get this thing, right? Actually this this chi comes here because it is the midpoint of both. So it's not either f of x or f of x1 or I mean f of z1 or f of z2. It is the the average f of z1 plus z2 by 2. So you have different kinds of methods, like different kinds of averages that you take based on different functions. Like you have those like you had like integration theory, taking rectangles, taking this, taking trapezium or whatever it is. So you have you have that those different theories, right? So here we take rectangles. So in terms of so chi j represents like your midpoint, and you're taking the rectangular method essentially. So how do you write that? Let's just sketch it out. So you have this. So this is so when you have a function, then you have g of j minus 1 and then g of j, right? So this point will be chi of z j. So this point is chi of gz, and now this point is this point is or simply written as chi f of chi j in other notation, right? Then you have like the rectangle here, and then you have this. So the area of this will give the a summation of these pieces is going to give you the total area of that particular curve, right? So now moving on, so we can have So we can have, we'll just convert it and express it as an integral. So we'll have limit as n tends to infinity, and of this whole thing of Sn is equal to integral of f of c dg. Right? So now we can write it down as integral of x comma x naught comma, so obviously this is bounded, so we will specify the limits as point g naught to c naught prime. So this is g naught and this is g naught prime, both are the upper and lower bounds. So we have x naught comma y naught and x naught prime comma y naught prime of u of x comma y plus I v of x comma y dx plus I dy, and then which is nothing but integral of x naught comma y naught x naught prime comma y naught prime of u of x comma y dx minus v of x comma y dy plus I integral of right. So given this, so we'll try to understand a couple of things. One, explicitly this is a function of three, is function of two variables. So you have x, I, y, and then you have a curve here. Okay, and this is actually in the third dimension, so it's like on a height. So like take this curve on a flat surface, and then you have a height, and then you have some sort of a function there. So that is one thing to keep in mind. Second, it can also loop in x and y, like it can form like closed contours. So these limits, so the boundaries, when you take x comma y, you can take the boundaries of like any kind of surfaces or region. These are called contours. So if you are taking a closed boundary where you are specifying like the function within, say, this entire region, right? So at each point of the region you have a function. You have at each x comma y you have an f of x comma y, right? So this is one more thing that we will come to be extremely advantageous. So unlike normal curves and normal function, your path also depends on the region that you're selecting. You can select it as a line, or you can select it as an area. So when we talk about selecting it as an area, we will see certain interesting things. So when we close the area, right? So this is called this is what you talk about as when you talk about contour integrating. So when you say instead of specifying 2 points, right? So instead of specifying a start point and then you have like an endpoint. So and the path in the middle. So this can be one kind of like a contour. So this can be one kind of boundary of a curve that you can take. Like, so if you want a curve, a single curve, you have to take a curve in the complex plane, and then that the function of that. So if you do that, it's a different thing, right? But if you take a closed loop, it's a different thing. So when you take a closed loop, so when you do this kind of like a straight, like when you just take a single curve in on the xy thing, a single this thing curve, then you have like your regular notion of integrals, right? So as are represented above. But the moment you have a closed like loop, so then you have contour integral of f of z. Now the idea is this result is known as your Cauchy integral theorem. Okay, so now let's look at a couple of let's look at the proof. Yeah, so let's look at the proof, and then we'll understand the proof with respect to here we'll understand the proof, and we'll understand the conditions that are required, and then we'll do a couple of problems on this, and that's basically it for today. So we'll just try to look at this proof and do a couple of problems, and by that we'll try to gain some insight. Tomorrow we'll use this particular idea to capture a lot of different things in complex analysis, and we'll see exactly what those are as well. So, right? Okay, so let's look at the proof. So for the proof, you need to take again. So you need to take this region to be everywhere analytic. So that means all the functions that are defined here are analytic. So it's a smooth surface. It cannot have any singularities. It cannot have any kind of like rough points. It cannot have it needs to be continuous and differentiable, right? So this whole integral region. So let me just put it up again here. So this whole region should be smooth analytic. That means C is an analytic region. Analytic region. C is an analytic region. So now so when you write the partial derivative, so the idea is that the partial derivatives of u and v are continuous. So essentially, then you have a continuous because of your Cauchy Riemann equality, like your Cauchy Riemann theorem, you can see how to re-express the whole integral using vector calculus, the Stokes theorem, to make it vanish. So then how do we go ahead with that? So just writing this down. So we have integral, the contour integral with respect to C, the contour C. It's a closed contour. It's a closed loop in the region xy, so it cannot be an open loop. That is another very specific condition. It must be a closed loop, right? So f of z dg is equal to integral of u plus iv dx plus I dvy. right? Which is nothing but the integral of u dx minus v dy plus I integral of v dx plus u dy, right? So now what we can see is we can write this like as like an integration of a loop around a loop in the xy plane. So what happens here is we consider these two functions here as vector potentials, or like as your vector fields or functions, like vector functions, and these are elements. So when you like talk about writing function or in a vector space, the function is necessarily, it gives you some sort of a potential, and the dx and dy give you some sort of a vector direction. So dx is the vertical direction, and dx is the horizontal, and dy is the vertical direction. So when you have this, when you try to think about this in terms of like vector fields and vector elements like vectors, unit vectors. So these are functions on our vector space. So x and y, dx and dy compose a vector space, and u and v give you functions on a vector space. So now, so how do we rewrite this? We rewrite this as rewrite this whole thing as we'll try to draw this. So of vx dx plus vy dy is equal to, so we are rewriting the Stokes theorem for the second term, right? Okay. Sorry. No, we are not rewriting. We are just rewriting the Stokes theorem. We are not using particular thing as of yet. We are just looking at the Stokes theorem. So v is a function of x, integral with respect to dx, and y is a function of y, integrate with respect to dy, is nothing but the area integral of dou vy by dou x minus dou vx by dou y of dx dy. So yeah, so we have the line integral becomes the area integral, right, which is just Stokes theorem. So then we have essentially rewriting this down. So we can already see what is exactly happening. So your vx, like before completing the proof, the idea here is that vx dx is so you don't have, so when you write down this integral here in terms of, so it is u dx minus v dy, so there is something cancelling out, so there's something so this thing, it cancels out, and this term also cancels out. So because you have so that's the essential idea. So let's just work it out, and we'll see that integral of u dx minus v dy, which is the first term, is equal to so the contour integral of vx dx plus vy dy, right, which is equal to the area integral of dou vy by dou x minus dou vx by dou y dx dy, which is nothing but negative of area integral of dou v by dou x plus dou u by dou y dx dy. Now evaluating the second term, we have integral of v dx plus u dy is equal to area integral of dou u by dou x minus dou v by dou y dx dy. So thus we have integral of f of z dz is equal to minus integral a of dou v by dou x plus dou u by dou y dx dy plus I integral of dou u by dou x minus dou v by dou y dx dy is equal to 0. So you have this term also vanishes, this term also vanishes, so the whole integral just vanishes for a smooth and continuous region, for a differentiable region, for an analytic. If all the if u and v are analytic like everywhere, if f of z is analytic everywhere within that particular contour, then you have the Stokes theorem holding here, right? There's also another interesting like you can, so essentially you just have the Cauchy Riemann expansion, and then you like say that your integral occurs only along the, so the idea here, more intuitively speaking, okay, this is the intuition, right? Like the full-blown just the intuition, and you don't have any mathematics here. So intuitively speaking, you just have like some region, okay. So what is this region essentially? It's a closed loop. So when you integrate, so what you're doing is essentially doing the line integral of some, like line integral of this with respect to some basis, okay, of the function here with respect to some basis. And for any smooth and continuous function, what you see is you come back and you travel around the closed loop. That means you essentially need to cancel out the, so you have 0, so you're looking at your circulation, so whatever is going in, okay, so whatever is like going into the region has to come out, provided there is no singularity. So essentially that's what we do here. So now given this kind of an intuition, okay, let's try to make a more literal sense of this whole thing with respect to with just a couple of examples, okay. So what we'll do here is we'll take the integral of z to the power of n. This is our function f of z is equal to z to the power of n on, we need to specify the contour. So contour is circle. So we like take a circular region in the complex plane, and then we integrate the function of z to the power of n on that circular region. Let's see what happens, right? So now what happens is integral of z and dz, where c is a circle of radius greater than 0 around z is equal to 0, right? So you can, whenever you take the contour, you specify the contour as going in a anti-clockwise direction. So yeah, so given that, now we parameterize this circle. We write down this circle as z is equal to r e to the power of I theta, and dz is equal to I r e to the power of I theta d theta. So you're writing down your z instead of like talking about instead of, so basically when we write down your g and dz here in this way, instead of x and in terms of x and y, we are maintaining a consistency, or we don't need to transform from a polar coordinates to, you don't need to transform from Cartesian coordinates to polar coordinates, because you're specifying naturally the boundary or this circle by specifying fixing r. So you can just fix r and you can specify the contour itself. So that is the particular reason why we are taking r e to the power of I theta. That is the polar form here. So yeah, as you know, this is how you represent the circle. R e to the power of I theta gives you a circle on the complex plane. So you essentially just specify r and you get your circle, the contour, right? So for now talking about z, so your contour integral of z to the power of n dz is nothing but I r to the power of n plus 1 integral from 0 to 2 pi of e to the power of I n plus 1 theta d theta, or with just everything in the same time, and then yeah. So this is, so how do you do this? Again, you can convert your contour integral problem to a line integral problem using the Cauchy Riemann, using the Stokes theorem. So you are converting your line integral in the complex plane to your contour integral to a line integral. So now that means you can specify the everything in terms of the single parameter theta, right? And of course so given that, also your r is constant here. So so you don't really need to specify that. You can just say r is a constant and then you can pull it out here. So essentially giving you the same thing, but then you have this equals I r n plus 1. Wait, no, okay. Right, let's just look at this, right? E to the power of I n plus 1 theta by I n plus 1 from limit 0 to 2 pi is equal to 0. So because you find out, so when you evaluate this, you find out that whole integral just vanishes. So how does that happen? So you have e to the power of I 0 and e to the power of I 2 pi, and you see that they just cancel out. So yeah, so when you say because e to the power of 2 pi I this thing by I n minus n plus 1, and then you have e to the power of 0 which is e to the power, so just you have minus 1 plus 1 and they just cancel out. So now given this thing, what we notice, one important thing to notice here is that we have a denominator of n plus 1. So that means this function is analytic everywhere except for all powers of z, except for the case where n is equal to minus 1. So we need to evaluate that case separately, right? So for n is equal to minus 1, singularity exists. So thus, evaluating for n is equal to minus 1, so you have integral dg by z, which is equal to I integral of 0 to 2 pi d theta, which is equal to 2 pi I. So you can actually work this out, but essentially, like what you count this as, so the idea here is really mathematically really beautiful, right? So talking about the idea, whenever you have a singularity, right? So what you do in your complex, so if you have a region here, and if you have a contour here, and the contour is singular at a point, at this point, so then what you do is you break the contour and you take it in such a way that you travel along the contour here, and then I need to disable this. So you travel along the contour. Assume that this is tracing the same thing, but then you create the same. You create a tiny little break here, an infinitesimal break here, and you traverse this distance, isolating the contour and then coming back here. So this gives you the same as the the area or the contour integral over there, except for that it removes the singularity at this particular point. So that is the visual intuition for this. So how do we do this? So this particular integral here, so z has a singularity here at n is equal to minus 1. So if you just substitute the value of n is equal to minus 1 here, so e to the power of I 0 theta, so that is 1 by I to the I into 0. So you just have a singularity here. So you can't so you can't really evaluate this particular thing, right? So what you do is to just say integral of integral of d theta. So you just say this is equal to 1, and then you just integrate d theta over 2 pi. So from 0 to 2 pi. So that means you have a tiny circle isolated here. And you just calculate that value of the circle, and that is a complex number. So it gives you a circle like I really don't know how to imagine this idea, because it's pretty complex. So it just comes out when you have it just comes out like this. So so maybe you can probably go into depth and figure out why it actually turns out to be just 2 pi I, which is the particular contour integral. But before going there, we'll just we will not necessarily go there, but we'll just look at another example and then see how this gives you something that is even more profound actually. So now what we want to do is we want to say that we have a square, and so this is in the complex plane. So this is x and this is positive y, right? This is our contour. So the square is our contour. So now the points of the vertices of the square. So obviously, because it is because it's an integral limit, you can separate your x endpoints from your y endpoints. I mean y limits. X limits can be separated out from the y limits. So basically, this is possible. So even though it is discontinuous, the contour itself is discontinuous. So because you can separate out the limits, you just have this particular square with the vertices minus 1 plus I by 2 and 1 plus I by 2, which is, so you have the origin here and then you have like a unit square around the origin. So you have minus 1 minus I by 2 and 1 minus I by 2, right? So these are the four labels, so four contexts. So you can establish the limits. So calculating the integral of f z to the power of n again. So we'll look at the example of z to the power of 2, and then we'll look at the example of z to the power of minus 1. So we'll consider these two examples. For g is g square. So we'll label our segments, right? We'll label this segment half to minus half. So which is half real to minus half. This is segment 1. So this is segment 1. So in this way, this is segment 1. This is from minus half to half. This is segment 1, this is segment 2, this is segment 3, this is segment 4. So we'll divide it into 4 segments like this, and then we'll have like the area of segment 1, the integral of segment 1 is equal to integral of minus half to half dx of x square minus 1 by 4 minus x, which is just you can work how this actually works out, but z square, this is just essentially z square, you can work this out, and then is equal to 1 by 3 of 1 by 8 minus 1 by 8 minus 1 by 4 minus I by 2. So you'll find out that you'll find out that this whole thing is equal to minus 1 by 6. And similarly for the area of like all the other segments, you have segment 2 is equal to I by 6, segment 3 is equal to 1 by 6, and again segment 4 is equal to minus I by 6. So when you add all this up, you have 0. So the net contour integral is equal to 0. Again, we will note that like whenever you're taking the limits, you're applying the Stokes theorem. So to just take the just to take the limits and not to take the entire, like we're just taking segment by segment, and instead of evaluating like the whole thing, right? So from here, but for the case of z is equal to z to the power of minus 1. Can anyone guess what the integral would be? Just take a guess. Yeah. No, but again, like we have a singularity here. If you notice, like again, z to the power of minus 1, we have a singularity, because when you express it in terms of your, so as we'll just try to do this, okay? So integral of z to the power of minus 1 dz is equal to I integral of, because you can, so how you can write this down in fact is you can write z to the power of minus 1 is equal to x minus I y by x square plus I square. Y square. So when you take the integral of like 4 Cartesian this thing, when you take like each of the thing, uh, notice that your, so you have this term as well, right? So you have the last remaining term, so you can check solve this out for yourself, but you'll notice that you have the singularity as dx of x square plus 1 by 4. So this term is like you need to take it around the singularity point. So essentially you will get is equal to 2I integral of du by u square plus 1, which is nothing but 2I notice any similarities here. Noting anything interesting? The thing is, so no matter what the shape of your contour is, if it has a single singularity, then you have the overall integral is equal to overall contour integral for a single singularity is f of z, let's mark it as 1, z1, if it has a like one single singularity. Dz is nothing but you have 2 pi I. So this explains this particular method that we have taken. So you can work this out actually. You can yeah, so it's not like none of these examples are fully like worked out. It's probably something that you have to work this out in order to like find out exactly what is happening at each point, because there is a lot of gaps, right? But essentially the idea is that when you take this thing, right, so when you have so when you convert this whole picture into the picture of vectors, so you can see that, so if you have a region and you have a particular vector field inside that region, okay, and the vector field is represented by arrows. So then no matter what the shape of the vector fields are, if your incoming is equal to outgoing in like all directions, right? If your total incoming, let's call this flux in, is equal to flux out, then you don't have any sort of like singularity here, because you cannot, like when you rearrange, so again we'll like look at vertices in differential geometry, like just a clear like just an intuitive picture, you don't have a singularity here. So when everything is smooth and continuous and analytic, you do not have a singularity here, and that means that you so there is no vortex form, not a vertex, vortex. So there is no vortex form, and like every this thing is continuous. So when you have like when you take any curve of the tangent, then you have something continuous. Here there's a lot of background noise, I don't think. You wanted to say something? Okay. So your vortex here is so there is no vortex here. However, when you take some sort of a and then you have some sort of like a vortex like region, then you do have certain incoming and outgoing vectors, like you do have a certain incoming and outcoming, will not define it what flux, but because of the singularity, you say that there is something present at the singularity. So if you apply the case of electromagnetism here and look at these arrows as like arrows indicating the electromagnetic field, what do you see here? Like how do you identify this particular singularity here? Look at the arrows. Look at the arrows. That should not necessarily. Okay. Or suppose you have, say, vectors that are coming out. Okay. So that are coming out like this. Or that are only going in. So you have a flux that is only going in or that is only coming out. To keep it simple. This is of course this is of course you can represent it as the flux around the the magnetic field around a circular pipe. But in more simple cases, what do these represent? And exactly. So you just have point charges. So these ideas are like you just have point charges. So this is how your point charges, the idea of point charges correspond to your singularities in complex analysis. So of course, you need to look at it a lot more rigorously in order to completely transcend from the concept of charges to your singularities of a function, because what is n is equal to -1, what is that singularity? How do you translate it to your physical idea of a charge? How do you go about what is a vector representation, what is all this? So right, of course the translation is not simple and direct, but we have the idea of a field which is given by u plus iv. So your u and v are orthogonal components of a field, and then basically around that you can define a singularity of the fields, and then you can represent some sort of charge, or in the first case you have some sort of a moving charge, right? So note that the charge has to be continuously moving, right? So it's current has to be continuously supplied through the pipe. You can't have one. So that means you need to take slices of different points in space-time in order to be to talk about a single electron moving, because otherwise you don't have a singularity in all these places except for where the charge is. So yes, in the first case it's that of a moving charge. In the second two cases it's that of a stationary thing. And notice how this is also a beautiful idea, right? Because once you say the charge is moving in or charge is moving out based on what the initial stationary charge is, so then you can also you see the magnetic field also coming up into the right hand, as per the right hand thumb rule. So you can so all these ideas are geometrically connected, and we'll look into that later. We'll try to look at geometric interpretation of Stokes theorem. But essentially the Stokes theorem and using the Stokes theorem in complex analysis to evaluate the Cauchy Riemann, using the Cauchy Riemann conditions, and then to evaluate the Cauchy integral of a point with the singular or without singularities, you arrive at this beautiful notion of having a number 2 pi I, a complex number, to denote any points of singularity. So this is called as the coefficient of the singularity or the residue. And then we will like later on we will just like try to express just just one spoiler, just a spoiler alert for the next lecture. So if you have like n singularities, so what you do around this region is you break this region down and create several point like incision, and then yeah, like it is here. So you have like a collection of singularities, and you have 2 pi I plus 2 pi I plus 2 pi I, or we'll talk about like what these numbers could be, but essentially it has like something like 6 pi I, and it gives you a number which is a constant. So no matter what your contour is, and no matter what your functions are, u and p like f of g is, the idea is like if you have singularities, and only based on the number of singularities that you have, your contour integrals make any sense. So that means you have something called as a topological constant for your integrals. So we'll try to evaluate the topological constants, and hopefully by the end of this whole series we should be able to step into a little bit of topology, and we should be able to evaluate some idea of topological constants, and yeah, we should be able to get that, right? So the idea is like in a topological, so how do you define topology? You say any simply connected region, that is any continuous and analytic region is is like topologically connected. So there is no singularity present there. So it can be shrunk to a single point. But the moment you have singularities, it cannot be shrunk anymore to a single point. So you need to take measure of the singularity. So for example, a sphere can be shrunk down to a single point. But a donut or a torus cannot be shrunk down to a single point. So you can have a circle around a single point, but then you still need to evaluate that circle. So that idea, right? So again, you have a circle, and you have I, the complex number, right? So you have a complex identifier for this notion of residue. I note that this might not, I don't think this is the case, because you will have some sort of like a different alternating, so you can construct some sort of a grading as to like, so for example, like if you have one singularity, and then you are taking a singularity, the second singularity around in a different direction, your notion of two singularities might cancel out, and you might get like 0 again. But then so you might have some sort of like complex grading involved, z grading, or like you have all those things involved as well. But that is slowly that is something for some other day. Yeah, so to keep in mind like how all of that origins, like as you go ahead, like you encounter like singularities and all of that, and to keep in mind how that arises, just remember that like whenever you have the Stokes theorem, and when you have a contour and you have a singularity in the contour, you can represent the singularity by a single number, and that serves as a like constant. So no matter what your functions are, no matter what your contour itself is, as long as you have that singularity, you can just denote it by a number and just get away with that. So right, with that we'll just end today, and tomorrow hopefully we'll like use this to evaluate a little more. We'll use this results to evaluate a little more complicated problems, and also as your homework, you should like try to understand and solve this particular problem, because I've done it in like I've just indicated the steps, but I've not like really solved the problem. So look at the integral of the power of n with respect to different contours, and look at how everything is defined, right? So you'll find most of the things, right? You'll find most of these problems solved. So just try to understand and go through that, and I think we'll pause recording for now.